Okay. So we're in chapter 8, as you can see. Let's go down to where we were. We're talking about paging. We talked a little bit about contiguous allocation, where everything is together. We talked about the problems of that. Then we talked about we defined external and internal fragmentation. We talked about segmentation. Segmentation is a way of dividing up the memory by conceptual groups. We talked a little about sharing of memory. And then this whole concept here of like jumping to different places based on the address, we're going to see, we use also paging. Let's go back to paging. It's this way. This picture looks kind of like this picture. Okay, so first of all, let's start with this slide. Yeah, remember, what's our goal? Can someone to remind me of what our goal is in paging and what our page table is going to do? No?
The accessing blocks.
Yeah, our goal is to introduce, in the words of this things that I sent you last night, to introduce an element of abstraction. Abstraction means that instead of having hard-coded the location of every memory, we have a logical address which will then get translated into a physical address. This guy in the video, he says one line that I like, which I've seen before in other places, but it reminded me of it, which is that every problem in computer science is solved by a level of by adding abstraction. Right? What we mean by abstraction is instead of having the actual thing have something like a pointer is abstraction. Instead of having the actual thing, have something that references the thing that you're wanting to get. Anyway, we'll see how this works again. So here's an address. This box, this square represents an address. And we're going to talk about addresses as 32-bit addresses, just because that's what you're familiar with from MIPS. But any address, of course, could be any multiple of 2, any power of 2. Could be like 16-bit addresses. In the exam, it could be 8-bit addresses just to make things easier, so you don't have such a big address. It could be a 36-bit. As a matter of fact, if you have a computer that's a 64-bit computer, that means it is a 64-bit address. So nowadays, computers are all 64-bit, which means their address length is 64 bits. On MIPS, it was 32 bits. That was the standard for 20 years because that's really a lot. 64-bit is huge amount of addresses. But so we're going to talk about all the examples. I think will be 32-bit. So for example, here's our 32 bits. In other words, if I would write numbers, I would say like this is 0, 1, 2, 3, blah 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 until 31. Right? And then I can put an arbitrary line here. This line can be anywhere. It doesn't have to be in the middle, but it could be anywhere. And that's why we call it P and D and M and N. And the idea is like this, that the page number is the ones and zeros that are to the left of this line. We're going to call that the page number, which is let's say it's only a 4-bit address, so to make it even easier. So let's say that there's 2 here and 2 here. So 2 bits are the page. So if it's 0, 0, we know it's page 1 or page 0. If it's 0, 1, it's page 1, etc. The highest page would be 1, 1, which would be 3. So there'd be 4 possible pages. And then the offset, this D here, is inside of that page. Where is the memory that I'm interested in? The actual byte that I'm interested in. So in our example that I'm just now saying, 2 bits here and 2 bits here, whenever you're analyzing such a thing, you're going to start with the right side. So we're going to say there's 2 bits here. That means inside the page, how many bytes can I reference? There's 2 bits to reference those. It can be either 0, 0, either 0, 1, either 1, 0, or 1, 1, 4. So the size of every page is determined by the page offset. The page offset is 2 bits, then the size of the page is 2 to the power of 2, which is 4. That's how many bytes are there. If the page offset is 8 bits, then it'd be 2 to the power 8, which is what, 256? Something like that. 256 bytes of addressable space inside each page. The page number, this part of the address, will tell me how many pages I have. Notice I have pages of memory and I have the size of each page. So that's what it says here. Page number P is used as an index into the page table, which contains the base address of each page. Page offset is combined with the base address to find the physical address that is sent to the memory node. For a given logical address space 2 to the M, where M, here, you see M is they didn't write this properly. They should have added a large brace here and say M. This whole thing is M, and this is M minus N size, and this is N. So if this is 32 and this is 18, then 18 and 32 minus 18 is 14. So this will be 14 bits, and this will be 18 bits. It has to add up.
What you said before.
What?
What you said before about the page size, like.
Yeah, you always want to know what the page. If you're analyzing memory, you have to know what the page size is. And the first step is always to start on the right side and say the offset, the possible number of offsets determines the page size.
And the offset is just.
If the offset is 2 bits.
What's the offset? Just how far from the beginning?
Well, maybe there's a picture. Let me see if there's a picture. Yeah, let's look at this picture. Let's look at this picture. Let's say that each of these is a page. Is it? I mean, page table. F. Yeah. Why is it called F? Because it's called a frame. When it's in physical memory, it's called a frame. When it's in conceptual memory and logical memory, it's called a page. So these are 3 frames of memory. So we've taken our memory. This is all our memory. And we've said that there's actually 3 pages or 3 frames. And imagine that each line here is a single byte. You can imagine each line is a single byte. So this byte is at location F, whatever this number is. If this number is 0, then it's here. If this number is 1, then it's here. If this number is 2, then it's here. So it's F, and then the first byte is 0, 0, 0, 0, 0, obviously. And the last byte will be F, 1, 1, 1, 1, 1. So in this example, there's a lot of zeros and a lot of ones. So this thing has got a lot of rows in it. But if we imagine that D is actually these zeros, and D is actually these ones. F is this F. So if we imagine that D was only 2 bits, then now my question to you is how many rows are here? So if there's only 2 bits, then it's only 0, 0, 0, 0, 0, 1, 1, 0, and 1, 1. So there's 4 bits here. So the size of D determines the size of the page. The size of F, or P, determines the number of pages that there are. In this case, because that's what I said. In this case, if there's only 3 pages here, then F can only be 0, 1, or 2, right? You never would have 3 though, because there'd always be a multiple of 4, or a multiple of 2, a power of 2. But in this picture, it's only 3, so this F could only be 0, 1, or 2. Now, how do you get the F? What this diagram is really trying to show is that I say, go to page number, I'll show you, I'll give you a really weird example to try to throw you an interesting idea. Imagine that the page was 10. So you go to page 10, wait a second, there's only 3 frames. But let's say, I go to say, go to page 10. Will it work or will it not work? The answer is it could work. Why would it work? Because if I go to this page table, which is a transform table, it's kind of like, here's a good example I never thought of before, which is like a train station. Yeah, I don't know if you guys know what a train station is, but there used to be such a thing as a train station. And you'd say, go to, I want to go to train number 2. And you'd say, well, it's obviously going to be on platform number 2. Why not? Train 2 will be on platform 2, train 1 will be on platform 1. Say, but that would be very limiting. That would mean that always train 2 has to be on platform 2. And what if we wanted to have, what if we only had 3 platforms and we want to have 4 trains? Then where would train 4 go? So we need to have the information booth. And we need to separate, we need to add a level of abstraction. We need to separate and say, I want to go to train 1, I got to go to the information booth and ask which platform is train 1 on? And it could be that train 1 is on platform 3. There's no necessarily guarantee. And then I could have train 10 could be on platform 1. There's platforms, which are the physical spaces that I can actually put the trains. I only got 3 of them, like in this picture. But conceptually, I can have as many train numbers as I want, many different trains to Baltimore, trains to Tel Aviv, long train to Tel Aviv, if you're in New York. So that's what this is. The page table tells me if I'm looking for page number 10, go to this table and go to row 10. And at row 10, whatever is written on that row is the actual frame to go to. That's why it says P this is the amount to go down. In other words, if this is 10, go down 10 lines. And then on this line, I'll see F. Whatever that F is the frame to go to. Could be 1. So it could be that I'll have 1, 1, 1, 1. It could be I'll have many times the same number, the same frame. But conceptually, the pages are different pages.
Could be different places in the frame or just the same information.
Oh wait, that's just the P. Inside the frame is the D, which I don't touch. The offset I don't touch. The offset is just copied and pasted. So where in the page? Of course, we're going to see a problem because, like, if I would have what I just described to you should ring some alarm bells because, like, what do you mean? If I'm going to have 10 and they're all going to the same one, but how do I know which if it's the right page for me?
Well, this is where you would switch things out, right?
This is where I have to switch things out, but how would I know? I'd have to somehow keep track that this is the wrong one. So we'll see how to do that. It gets complicated. But at the moment, we can just think of it as there's only 3 rows in the page. The simplest version would be 3 rows in the page table, and it tells me where the pages are. So that way I can have, I can put page 1 in frame, 0, 1, or 2. I don't have to put it always in the first place.
The page table is always like a table, or can it do like an operation like modulo or something?
Well, it's a table. It's a table. We'll see modulo. Modulo is actually going to work. It's going to figure into this, but it's not that it does. It's a table. The operating system has to do modulo. The table is a table. The one key point that it gets lost on a lot of people. Oh, wait a second. Page table. Yeah. Okay. I'll just leave it like that. Okay. So that's our page table. So let's go on. So here's just an example. Paging model of logical and physical memory. So you see page 0, 1, 2, 3, 4. And here we're doing the opposite case where we have many, we have a huge train station that was built in the 19th century that's designed for lots of trains. And now we only have like 2 or 3 trains. So we have all these physical memories. And our page table is going to tell, we only have 4 pages of logical memory. But so that means page 1 can go anywhere. So page 1 is going to go, well, what are we going to do? We're going to go to page 1, which is here on the page table. Means go to row 1 in the page table, and we see a 4 there. That means it's going to be logical. It's going to be physical frame 4. Go down 4, and here it is, page 1. If we want page 2, we're going to go down to row 2 and say 3. So we can go here at 3, and there's page 2. If we want page 0, we're going to go here and see a 1 there, and we're going to go down 1, and here's page 0. So now what now if you can imagine, this is the page table for, I'm going to go one other step further. If you understand this, I want to add another point, which is, what if I had 2 processes now? I could have 2 processes. He would have his own logical memory and his own page table. And now what we would do is we would say, hopefully the numbers would be different. As he would also have page 0, 1, 2, and 3 in his page table, just like this, but in his logical memory, but his page table would be different. When he goes to 0, it wouldn't say 1 because that's being used by somebody else. It might say 2 because that's free. In his row 1, it might say 0. In his row 2, it might say 5. In his row 3, it might say 6. And then from a logical perspective, from the program's perspective, he has his memory in order in these pages. But physically, they're spread out throughout the memory, anywhere we want. So that works well as long as we want to have the program to have a less memory than the total memory of the machine, right? As long as he's using a subset of all the memory, then we can squeeze in many programs into our physical memory, and each program would feel as though he has a contiguous memory. And so we're actually getting non-contiguous physically, but conceptually contiguous. And that's what we want. Because when we write our program, we write it contiguously. We imagine that I can jump 4 lines ahead in my code, right? If I want to say, do my loop, jump, or the loop breaks, so jump 4 lines down. So I want those 4 lines to be contiguous. I don't want to say, oh, wait a second, my page is here. Jump 10,000 lines because I don't want to have to know where it really is in memory. I want to be able to jump around in this memory and let the operating system put it where it wants and let there be some kind of translation. So that gives me the best of both worlds. I have contiguous logical memory and physical memory is not contiguous. Why is this different from this? Here, what does it say? N is 2, M is 4. M, remember, is the whole thing. So why is he saying?
Is it just showing each individual byte in each page, or before it just showed the page?
Yeah, I think so. Yes, I think you're right. Yeah, that's obviously true, but I'm trying to think if there's anything else he's trying to say. 32 memory. 4-byte pages. All right, he did exactly what I did. He said 4-byte pages, like that's the simplest one to think about, right? A 4-byte page where n is 2, therefore the other side is also 2, 2 and 2. And what is he saying over here? Here's a page. In other words, here are the 4 pages. This one is page 0, page 1, page 2, and page 3. 4 pages. And inside each one is byte number A, B, C, this is the content. So these are the bytes. This is the content of the bytes. That's not the names of the bytes. The name of the byte is 0, 1, 2. So here I see it as contiguous. And here, A, how am I going to find A? I'm going to have to jump to page table. Well, this is 0. So I'm going to go to row 0, and I'm going to see 5. I'm going to go down 5 pages, 0, 1, 2, 3, 4, 5, and there's my A, B, C, D. See it? A, B, C, D. Exactly what I explained to you before. It's just giving the details of the content. Okay. The only thing that threw me is why he says 32-byte memory. That's kind of irrelevant. Well, 32-byte memory. Oh, I see. The whole memory is 32 bytes because this is 4 and 4 is 8. And 8 and 8 is 16. That's 16. Why is it 4?
No, the physical memory.
Oh, the physical. Thank you. Okay, the physical 4-byte. We have 4 bytes. The logical memory is 16 bytes, but the physical is 32 bytes. Thank you. Okay.
Can I ask?
Okay. So calculating internal fragmentation. Why is it? Page size is. Okay. Here, remember we said paging is going to have internal fragmentation? Why does paging have internal fragmentation?
Because things can be removed and then.
Because if I allocate, because back to this picture, or actually better is this picture. If I'm giving this program, let's say this program uses all of this, but only half of page 3. It's all he needs. But I still have to give him all of page 3. It's like if I have if I'm taking notes and I I need 3.5 pages. In the end, I have used 4 pages because I can't use a half a page. It's going to mean I'm not going to rip the page in half. So I have, if I'm taking notes on paper, I'm going to have 4 pages of notes, even though it's really 3.5 pages. That's internal fragmentation. So we're now just doing an example. I think this is just an example. So let's look at this. Imagine the page size is 2,048 bytes. Ellie Chevy raised a hand, but I can't hear you, so you better write a message. Or send a message to the WhatsApp group, that's better. Let's see.
It's in the voice note.
Oh, I see. I see. Elana Weiss. Who's Elana Weiss? Yeah, it's the regular things. Anyway, if you have a question, you can send it on WhatsApp. Okay, so what is 2048? Well, the number that should all be in your heads is 1024, right? Right, 1024 is 1 kilobyte. 2 to the 10th. 2 to the 10th is 1024. So this is 2 to the 11th. This is times 2, 2048.
It's like that game, 2048.
I don't know that game, but yeah. Okay. So the process size. Here's our actual size of our process. And what do I mean process size? How big?
Chevy just asked the question
Yeah.
in the chat.
Oh. How does it work with different programs having the same logical address so they come to the page table with the same address? So excellent question, Chevy. But the answer is that, I actually did answer it. The answer is that there will be multiple page tables. They won't come to the same. This is that's a kind of a mistake in this program, in this diagram. This page table should really be labeled page table for process P, for process P1. There'll be another page table for process P2, and his numbers will be different at 0, 1, 2, and 3. In other words, they don't have the operating system in this, right? The operating system maintains a page table for each process. Okay, so let's go to this example in math here. So each page size is 2048. The process size is 72,768 bytes, some number. How are we going to figure out how many pages we're going to have? Simple math. How will we
Divide by 20.
divide? Everyone sees that? If the total size is this, and we know that the page size is this, how many pieces of notes we have? We can fit 1,000 words on a page as we write. And so if we have 1,000, if we have 10,500 words to write, how many pages will we need? 11 pages. So how did you do that? You took 10,500, you divided it by the size of a page, which is 1,000 bytes, 1,000 words. So here we're saying that the size of a page is 2,048 bytes, and the total size of this process is 72,000. We divide 72,000 by 2,048, and we get 35 and a remainder. The remainder is 1,800. It's about 1,086.
So it's not going to be a full page.
So how many pages do we need? Well, we're going to need 36 pages, right? The remainder we can't just stick exactly. We're going to have to put it on a whole page. So we're going to need 36 pages. But now the question is, how much fragmentation is there? How much of that last page are we not actually going to use? So that's subtraction. 2,048 minus 1,086 is 962 bytes. So that is the amount of internal fragmentation in that example. What's the worst case fragmentation? That we needed a multiple of 2,048 plus 1, right? We need one more word. You can't just squeeze it onto the bottom of the previous page. You have to take a whole new page and write that word there. So the worst case is one frame with 1 byte in it. So the worst fragmentation could possibly be 2,047 bytes of internal fragmentation. So you can see actually that the smaller our pages, the less internal fragmentation. To the absurd point that if we would have pages of 1 byte, then we would have no internal fragmentation. But that would be crazy because we would have a huge page table. On average, fragmentation equals 1/2 the frame size. Well, that makes sense, right? If it's random, if it's always a random number, right? Right? Everyone sees that it'll be half. If sometimes you'll have one, sometimes you'll have almost nothing. I'm sorry, sometimes you'll have 1 byte of fragmentation, sometimes you'll have almost the whole thing. Sometimes you'll have so if you average all the possible cases, it'll be half. There's the average case of 50% is used and 50% is not used. So small frame size is desirable, question mark? Well, no, because we're gonna have other problems with small page, but more or less small. That's why we have pages that, like in the old days, they used to be about a half a kilobyte, 512 bytes. But each page table entry takes memory to track it, right, exactly. I say the best case would be, that's what I said this all very quickly. I said, if the best case would be have pages of size 1 byte, then I'll have no fragmentation. But then I have to keep, imagine if you had pages, imagine if you, in other words, index cards. Index cards are better. You'll have less wasted pages, you'll take notes on index cards. Say, I want to do it. I'll do it on those little Post-it stickers that, you can get. I'm gonna try 1 word on each one. Then I'll never have any wasted space. I'll just write on, but the problem is I gotta keep track of where all those little Post-it ones are. So that's exactly the point. It's the same reason that a page size in a notebook is a certain size because it's easier to keep track of. Even index cards are harder to keep track of. So we want a certain size. We want the sweet spot that it's not too small that it's hard to keep track of, and not too big that it's going to cause a lot of internal fragmentation. That's what it says here. But each page table entry takes. In other words, I just want to make that point again. If I have lots of pages, then this page table starts to get long, right? This page table here in the diagram, it starts to get long. I gotta have lots of pages. If I have the same 32 bytes of memory, and I gotta have a page for each byte, then I have 32 entries in my page table. And that page table is actually sitting where? In memory. So I'm wasting memory on that. So it's true, I don't have fragmentation, but I have wasted memory on the page table. Okay, page sizes grow over time. Solaris supports 2-page, this is already from 2013, but Solaris supports 2-page sizes, either 8 kilobytes or 4 megabytes. That's quite large.
How do you know the size of the page table on your computer?
I don't know. Good question. I don't know. Processes view, I mean, you could probably just Google Windows 11 or whatever, Windows 10 page size. And it'll probably be,
It's not based.
it's
on
probably
your,
fixed.
It's not based on individual hardware.
No, it's probably fixed in the operating system. Here he's saying that Solaris is unusual in that it supports that you can configure it to have 2 different sizes. But usually it's a decision made by the operating system. If you work for Microsoft and you were the designer of that part of the operating system, then you would have to make that decision. Processes can process view and physical view memory now very different. Okay, right, we said that. By implementation, processes can only access its own memory. Right. In other words, the operating system, because once we have this page table, it now comes out, we've also gained another thing, which is that this process here, this is the memory of the process, A, B, C, D until P. He can't get to this page in blue here, this 16 page. This page is size of 16, he can never get there because to get to any memory, he has to go through the page table, and the operating system is controlling that, and he can never get to this other memory. No matter what jump he does, he tries to jump 100 forward, I'm gonna jump so far, I'm gonna get to the next program. It won't happen, it's impossible, because he has to go through the page table. The page table limits him to certain places. So we've also achieved another one of our goals, which is protecting the memory of one program from another. One program shouldn't be able to get out of its area that it was defined and affect the behavior of another program. Okay. Okay, here this is very simple. It's just showing you actually that there's a free frame list. The operating system has to maintain which frames here in gray are unassigned. In other words, there's a process that's already using 16, 17, 19, and 21. Comes along a new process and says, I've got logical pages 0, 1, 2, 3, just like every process has logical pages 0, 1, 2, 3. I want pages. So the operating system will have to assign him a page table and make a new page table. And here you see, he gave him 14, 13, 18, and 20. So now the free frame list is only got one left, 15. You understand? The picture looks confusing, but it's really pretty obvious.
What's the blue? Blue is also used.
The blue is some other process that was already there. In other words, in this picture we have, in A, we have some other process using 16, 17, and now comes along this process. And notice this is the free frame list, 14, 13, 14, 15, and 20. Why isn't, and 18, and 18 also. And he chooses, I don't know how, but he chooses 4 of them randomly, or maybe the first 4 in order. He took the first 4 in order, and after 15 was left available. Okay. So the page table is kept in main memory. There's something called a page table base register, points to the page table. In other words, if you've got a page table in memory, right, this page table is also in memory. Which memory is it in? It's in the same memory here. So it's on some page, right? It's got to be on some page. Maybe it's in page 16. Maybe this blue, let's answer it differently. Let's say this blue is the operating system itself. The operating system itself is also occupying memory. So in the operating system itself, he has to have reserved space set aside for page tables that he's going to create. So this page table is, let's say, in 16 here in the operating system. Okay. And in order to find it, the operating system has to keep a list, in a list of all of his processes that he has to have also where the page table is for each process. So that's the PTBR, page table base register, points to the page table. Page table length register indicates how long the page table is for that process. In this scheme, every data instruction access requires 2 memory accesses. 1 for the page table and 1 for the data instruction. In other words, all right, we're already seeing that we're getting a problem here. If the operating system, I mean, not a cost, everything comes at a cost. We have this wonderful system, but now in order to get to a certain place in memory, I've got to first do a memory read. I got to do a load word from the page table, right? I've got this pointer to my page table for this process. Every time I want to do a jump, I've got to first read the page table, or I want to do, let's say, a load word. First, I got to load the word from the page table, and then I get the actual address, and then I got to do the actual load word. So it's going to cost me an extra memory access. And a memory access, if you recall, is slow. It's slower than reading from a register. Register is very fast. This is actually going to the big memory store and getting and reading a piece of memory. That's a slow action. So the 2 memory, so 1 for I got to read the page table, and then I got to actually read the instruction, the line of code at that place. Right when I instruction fetch. Remember instruction fetch from operating system? The first step is instruction fetch. I got to do the instruction fetch. That's also a memory read. So I got to do 1 for the page table and 1 for the instruction fetch. The 2 memory access problem can be solved by the use of special fast lookup hardware cache called associative memory or translation look-aside buffer. We learned this in MIPS, TLBs. You have a TLB, which is a translation look-aside buffer. Essentially, instead of keeping the page table in regular memory, what is cache? What is another name for cache? We called it near memory. Because near, in the sense that if New Jersey is near New York, you get there quickly. So quick things are near, it's called near. So cache is near memory. And because we can access it faster. So then the page table won't actually be in regular memory.
No, where does the cache come from? Where's the cache reside?
Cache is not in this picture, but it would be another piece of memory.
But then you're still using pieces of memory, so you're still using
But it's
memory.
special, we'll add some special memory, some special fast memory to the CPU, just for solving this problem of page tables. Since we've introduced page tables now, we're gonna have to make them as fast as possible. So we're gonna sort of put some turbocharged memory into the computer very close to the CPU. Figuratively and physically close. Some TLBs store address space identifiers. Sorry, that's not important. The TLB is typically small, 64 to 1,024 entries. So in other words, it won't be that big because it's going to be very fast. On a TLB miss, so what if you tried it? So it's going to come out like this. Now we're going to start talking about this whole thing. Since we have a whole cache issue, which is the idea of cache is that you don't put everything into the cache. You just keep. This is a review of exactly what Abby taught you. Is this ringing bells a little bit? The cache, you can't put everything in the cache. So you sometimes have a hit and sometimes you have a miss. You're looking for something in the cache. Either it's there, in which case you're lucky and you can keep, and everything goes fast. Or you have it's not there and then you have then it's slow. You have to pay a penalty. It's called a miss penalty. There's Miss Universe, there's Miss Penalty. Miss Penalty is that you have to now do extra work. You have to go load it from memory into the cache and then read it from the cache. It actually take you longer than if you just looked directly in the cache because you didn't find it there. You first looked in the cache, then you didn't find it. Then you go to memory. Now you're going to not just look at it in memory, you're going to actually copy it into the cache, then reread it again from the cache, and then continue on your merry way. But you now have to pay that price of having a miss.
So we really only ever read from the cache.
Yes, we only read from the cache, but no.
I mean, we have to put things into the cache, but we'll never read.
If it's a miss, then we'll copy into the cache, then reread from the cache.
And then if it's a hit, then we're just reading.
But you're reading from when you're taking it from the memory and you're copying from memory, that's called a read also. So you're reading from memory.
But we're only ever using the information from the cache.
Yes. We're not going to read we're never going to say, oh, it's not in the cache, I'll just read it from memory and leave the cache as it was. You have to put the cache, you have to fill the cache and then reread the cache. So on a TLB miss, the value is loaded into the TLB for faster access for next time. In other words, we're basically we're going to put it in. We're saying since we recently used it, we're probably going to use it again. Let's keep it in cache. Replacement policy must be considered. We have to decide who to kick out of the cache if the cache is full. So now we have to choose a victim to remove from the cache. I'm going over this quickly because you all know this, I hope. Anyway, some entries can be wired down for permanent fast access.
What is wired down?
You don't have to know that, but it just means that it's hardwired. That's what it means. Somehow it's hardwired. That memory is always good. Like a certain place will always go to certain entry in the table.
That defeats the whole purpose of replacement policy.
Yeah, I don't know. Some entries can be wired down for. I don't know what that is. Not important. Wait, why is this associated? All right, I don't want to deal with this right now. Here, let's go to paging hardware with the TLB. So now we're back to our same picture, but we've thrown in another table. You see that? This is like this picture. It's like this picture, same exact picture. There's only one table here. Here there is an added table, and that's the TLB. And it's just saying that first we're going to go into our TLB here and see if P is there, page number. And it could be, in order to do this, now, there's an important point you have to understand here. In the page table, we wanted P was, let's say, 7. So what did we do? We have this brace here. We counted down 7 rows, and we know that we need frame number, what's on the 7th row. But if the cache is only some of the memory, then we have no way of knowing where anything is. It can't be that we have it all there. We can't go down 7 pages. Notice there's no brace P. We're not going down a certain number of rows. We actually have to check every single row and see if it's the one that we're looking for. If we're looking for 4, if P is 4, 4 could be in this box, could be in this box, could be in this box, could be any of these boxes. We don't know. So we're going to do a parallel check. And this is done in hardware. This is, again, Avi did or should have explained this to you. We'll do this hardware for checking. We're not going to do a loop like you would in software. We're going to check simultaneously all these places. Whoever is the accurate one, we will produce the hit and we'll get the frame number that we need and we'll append that to our D, to our offset, and get the actual physical address. If there's a miss, we'll have some indicator here that will tell us that we didn't find 4. 4 wasn't here. Then we'll have to go to the memory here and to the actual page table and go down 4, and then we'll for sure find it. Now this diagram is not accurate because it doesn't show the writing back to the page table. It doesn't show reading directly from the page table again, but it's conceptual. The idea is that if it was a miss, then I'll get it from the page table, but I'll also write it back obviously to the page and also remove somebody from the TLB. There's also validation, valid bits. We're not going to go into all the details of this, but there's valid bits. I'm just reminding you maybe. There's a valid bit to tell me if the entry is a real entry or if it's just a leftover from some previous incarnation. Okay. Yeah. Did you do this also with Avi? Effective access time? I don't know if you did
I
this.
don't think so. I think he did a lot of theoretical stuff with page tables, because that stuff wasn't on the exam, so he was doing more of the theoretical, not so much.
Okay. This is just simple algebra here. We're just talking about what is the effective access time? Because if you look at this picture, sometimes the access time will be the time it takes to get it from the TLB table and then reading. And sometimes it'll be getting it from the page table and then writing it to the VLB. So it'll be longer. So the effective, when we talk about effective access time, what we mean is average. On average, what is our, how long does it take us to get a particular piece of memory? So it can be less than 10% of memory access time. So, okay, the hit ratio. So alpha is going to be our hit ratio. The percent of time that a page is found in the associative register, in the cache. That's another way of saying cache. It's a ratio related to the number of associative registers. The more, obviously, the bigger the TLB, the more hits you'll get. Consider an alpha, so here it's given to you. You're given an alpha of 80%. In other words, 80% of the time, you're finding it in the lookup table, in the cache. An epsilon, or whatever that is, I don't know what that is. Anyone know Greek?
It might be epsilon.
What?
Might be epsilon.
It might be epsilon. Looks like an E, so epsilon sounds good. Let's call it epsilon. Epsilon is 20 ns. What is ns? Nanoseconds. What are the 3? U is, microseconds is ms. What is a microsecond? Micro.
Is it a millisecond?
Oh, sorry, ms, you're right. Ms is a millisecond, thousandths of a second. And
The
mu, which looks like a U, is microseconds, which is millionths of a second. It's very confusing because mille, in Italian, mille is 1,000. So millisecond is 1,000th. But we think of milli sounds like million, but it's not. It's 1,000. Okay. So it's 20 ns, nanoseconds, which is what a nanosecond, not a million, but a billionth of a second. And it's 100 nanoseconds, right? 5 times as slow to do a memory access. So the effective access time is, remember we said that it's, alpha is 80%. So that means 80% of the time we have a hit ratio. So 80%, so here's alpha. This is like a general formula. Here's the actual one. But let's look at the general formula. The general formula is 1 plus the time it takes for, this is the, I hate this way they do this. It's confusing. This equation, they don't derive it here. I'm not going to derive it with you, but you have to, really we should derive this equation, how they got to it. Because it's a little bit not intuitive. But the alpha is 80%. So, what?
Why? That's just.
80% of the way, let's go slowly. 80% of the time, I have a hit. So what's a hit? A hit is, well, reading from memory. This is like, let's say, reading from memory, and this is the reading from the TLB. Because I need to read the actual memory, and I need to read the TLB and then read the access memory. So let's call it 1 plus the 20 nanoseconds. And then it's also 1 minus alpha. Remember, alpha is 80%. So 20% of the time, I got to do 2 memory reads. Because I got to read from the table, and then eventually I'll read from the actual place, right? I got to read from this table, which is memory, and then I got to read from the actual physical memory. So if I had a hit, I had 1 read from here and 1 read from here. If I have a miss, I have a read from here and a read from here. That's 2 plus the TLB. So let's see that again. It's 2 plus the time to read from the TLB times the percent of 1 minus 8. And that you can compute to being 2 plus epsilon minus alpha, which is the time minus, no, this doesn't make any sense actually. What does that mean? 2? Wait, what is 2?
The amount of read.
It should be the amount, 2 times the amount of read. Time, where's the read time here? And what is minus alpha? Alpha is alpha is 80%, 0.8. So it'll be 2 plus 20 nanoseconds minus 0.8. What's the units? What are the units here? It's a little bit weird. Consider an alpha of 80, 20 for the 20 microseconds and 100 nanoseconds for memory access. Okay. So the average time will be 80 times right. 80 here what he did here is this whole equation is silly because look what he does here. He does 80% of the time. It's just the memory. I'm ignoring the TLB. It's just the memory access. And 20% of the time, it's 2 reads. So what do I get? I get 80 times 100 is 80. 0.80 times 100 is 80. Plus, well, this is like 2 times 4 is 40. So 40 plus 80 is 120. So what is he doing here? He's just saying 20% of the time, I have to do 2 reads, and 80% of the time I do 1 read.
That looks a lot less complicated.
It looks a lot less complicated than what he did here. Why? Because he ignored the TLB search because it's small, although a little bit weird. You just right? You agree with me, Zahava? He ignored the epsilon. It should be really 120. It should be really 140 because there's at least one reading of the TLB. Actually, there's a reading of the TLB here, and there's 2 readings of the TLB here. So it should be but that's constant. You see, here there's right. All right. You know what he's doing? Why he's removing the access time for the TLB because that's constant. Like there's just basically 1 times that. There's always going to be 80% of 20, and then 20% of 20. So it'll be 100% of that. So you could really just add on 20 here. It should really be 140 plus 1 more read, whatever. It should be 140. Consider a more realistic hit ratio where epsilon is 99%. So then what would we get? We get 99% of the time it's 1 read, 1% of the time it's 2 reads, and we get 101 nanoseconds.
Why is that more realistic?
Good question. Why is it more realistic? It seems like that's
I mean,
like
you have a massive
ideal.
cache.
What?
It sounds like you have a massive cache then.
Right. Well, we want to create. For designing a system, we really want to avoid having to read memory a lot. So we will. This is more realistic in the sense that we are going to design the hardware such that we have enough cache, such that we get a hit ratio of 99%. We're going to do everything we can to get a hit ratio like that. You're right. It's more like an ideal. It's not like a realistic, but we're going to design it in such a way that we can reduce our effective access time as much as possible. Yeah? So it's just, right, basically we're just going to make a larger cache. And then you notice that basically the access time is exactly the same as a single memory read because the amount of times that we do a double memory read is so small. All right, that's enough of that. Okay. Now let's look at, I'm skipping a slide, but I'm going to this slide. Let's say, and then we talk about this valid bit. So we're going to talk about this valid bit now. Because I could have, let's say like this. Let's say that the page table is a fixed size. In other words, every process is going to get a page table of 32 rows. But it could be some programs are just hello world. And they don't need so many pages of memory. But they're still going to get a page table of a fixed size, of a large size. So then, when the program is actually compiled and the operating system sees, oh, this compiled program is only 20 lines of assembly code, I can squeeze it into 2 frames. So he's going to mark some of the frames in the table as invalid. And that's this I here. You see that? Valid, invalid bit. It's really not a V or an I. It's really a 1 or a 0. It's really valid is 1 and invalid is 0. But you can think of it either way. Valid and I is invalid. So this is saying that frame number 2 is valid. Frame number, if he wants to go to page 0, 1, 2, 3, 4, 5, that's in his logical address space. And here's the page table, but places 6 and 7 are unassigned. Everyone sees that in the picture? They're unassigned, and therefore they're marked as invalid. This is called cat. This is invalidated.
I means invalid?
I means invalid. Okay. V means valid. I usually see it, it's usually written as 1 or 0.
But 7 has something.
What?
7 has page 3.
No. 7 is here.
Oh.
Frame. This is frame 7.
Right.
It's funny, he did this differently. Now he did it gray and blue. Blue being, well, blue, what's blue?
Operating system according to the last answer.
Let's take it up by other stuff.
Or other stuff, yeah, other pages. So we won't let him go. In other words, why do we put an invalid here? Because if he wouldn't have an invalid here, what would he do? If he tried to get to page 7, page 6, he would go to frame 0. But somebody else is at frame 0. And more than that, the page table could have the garbage in it from the last time. So I need to, you know what I mean? There'll always be a number here. There's never a blank line. Even if it's 0, 0 is something, 0 is a place. He'll try to go to page 0. And if it's not 0, it might be garbage from some previous use. So I need to mark it as invalid. So what did he write here? So this is the previous slide to introduce that, what we just saw. Memory protection implemented by associating protection bit with each frame to indicate if read-only or write-only access allowed. Because remember, it could also be more complicated than just valid and invalid. It could also be that you're allowed to read it, but you can't write to it. Because it could be a shared, it should be a function that's shared between 2 different processes. And then they both can read it, but they can't change it. Invalid bit attached to each entry of the table. Valid indicates associated page is present in logical place, and thus legal page. Invalid indicates the page is not legal. Okay. Or use page table length register. Fine. Where you could have a register that tells you how long the page table is, right? Notice that the pages that are invalid are at the end. So I can just have another register that tells me how big it is. And then I know to stop. But the other way is to just mark it as invalid.
How did we get here? How does this result from switching some programs into less memory?
If we wanted contiguous memory, then we had a problem, which was that we would get holes in our memory, and we might have this piece of program that's like that there is enough memory free to use to put it in, but we can't find a contiguous location for it. So then we're stuck. We can't put it in. So by making pages, we are able to use that space that's not contiguous and make it seem contiguous to the program. That's why we're doing this.
But you were saying, because you said like if we have a fixed page size, then sometimes when we have a program that really doesn't take up a lot of space, then we could like save it in only a minimum amount of space, and then.
Oh, you're confusing. Your sentences are getting lost.
I don't know.
I said a fixed page table size.
Yeah.
Because theoretically, the page table should really be the size of all the frames. In other words, well, no, it doesn't have to be. It can be smaller. Whatever. The page table size is a certain size. We would like it to be sort of large so that we could accommodate large programs. We could have a variable size page table, and that's kind of what he says in this slide, in the previous slide here, where he says we could have a PTLR, page table length register. We could have variable size page tables, but then we'd have to know how big each page table was. So we'd have to have some kind of register to tell us, and that would be the PTLR. But in this picture, he's assuming that we are not having that PTLR, and we're having fixed size page tables, but yet some programs don't use all of their memory.
Right.
So we need to know which entries are invalid in case the program tries to access memory that it should be going to.
I don't get that part. How does that have to do with some programs not using all their memory?
No, they're using more than their memory. In other words, let's say I read a 3-line program, and the third line of the program is jump to line 70. That shouldn't work. I only have 3 lines in my program. You see what I mean? My program is 3 lines, and I say now jump to line 70. At the third line, I say jump 70 forward. There's nothing. There's garbage there. I didn't write anything there. That's a bad program. I wrote a bad program. But not only, but it could now if you're the only one on the computer, then as they say in Yiddish, nicht gefährlich. It's not dangerous. You know that expression?
No.
Nicht gefährlich. It's not dangerous. It's not dangerous. So you jump 70 ahead. And there's some garbage there and your program crashes. But it could be a lot worse if you've got lots of programs there. It could be you jump 70 ahead and you land on somebody else's program, some other code that's actually in memory, and you start running that program. And then your program starts doing other things. Maybe you jumped into the operating system and you start doing some other thing. So we need to prevent you from jumping to places that you shouldn't be jumping to. So we're gonna write in the page table that that's invalid.
Oh, because if a program doesn't use its full page table size, but since it's.
In other words, if I'm on page, if I'm on, wait, maybe, yeah, wait, if I'm. In other words, in this picture, really, this is the actual program. These are the actual lines of the program. But if on page 5, I say jump ahead to logical space 70, way down here. So he's going to calculate, well, that must be page number 7. So he's going to go to page number 7 and try to go there, which is 0. So he's going to go to 0 and do whatever over here. But he's going to get stopped from doing that because he's going to see the invalid bit. So therefore, if on page 5 I say jump ahead 70, the operating system won't let me do it. It'll crash my program, and it won't run whatever code is in page 0.
Meaning because each page table size is fixed, then it might think like, oh, this exists, so I can go there, but no, you can't go there because it really is supposed to be empty.
Right.
basically.
Exactly.
I see.
All right, let's go forward. Oh, this is. This is just showing that let's see. Page table for process 1, page table for process 3, page table, what is this process? We have 3 page tables here. We have 3 processes. 1, 2, 3. Notice that the actual code is lines of the editor program, let's say, and it's the same code. But what we're going to do is say that when he wants to do the editor, go to look at the 3 here, a 3 here, and a 3 here, because the editor actually starts at frame 3. So you see what we're getting here? We're actually having 2 programs that are using the same function called ed, and we don't have to put it into memory 3 times. If we would have contiguous memory, we're talking about another advantage that we get. A second advantage we get is that we can share code easily. We just put in the page table the same frame by 2 different guys. As long as they can't write, as long as we add some kind of entry there that says no writing allowed, then they can actually share code between them. So from my perspective as pre-1, this is my program. And I have all those pages that I want. I have page 3, 4, 6, and 1. And he has also 3, 4, 6, and 7. Each have their own separate parts, but they all share that same part. And that saves a lot of memory.
Will there be a time when they would share it, but it wouldn't be done all together because because each individual process would need to write to it?
If they need to write to it, I don't see how you would share it.
Right, but then you'd still be like, the code itself, though, I guess the original editor code will still be the same for each one, but then throughout the process, they're each going to be changing it. So you're still.
You could have a copy, there's something called cow, copy on write, where when I want to, I can put it into memory, we talked about that before. When I want to put something in memory, when I want to like write to it, all of a sudden I do want to write to editor 2, then all of a sudden I'm going to have to, operating system has to give me a new piece, a new frame, and copy ed2 into that new frame and let me write there. And now I've got my own section of that code if I want to write to it. But that's just an extra complication. Okay. Right. So now we're going to talk about another question, which is how big are these page tables? And he talks about that in the video that I sent you, Erev Shabbat. How big are these page tables? If we would have the page table for every single, if we'd have for every single byte, then it would be huge. that's what he mentions that in the first video I sent you. The first video is the most important one, I think. Okay, let's think of this. Here we're just discussing this, the dangerously large size that a page table may get to. Can get huge using straightforward methods. Consider, for example, a 32-bit logical address space as on modern computers. Well, nowadays we have 64 bits. It's a little bit old. And a page size of 4 kilobytes, which is actually pretty normal. 4 kilobytes page size. Remember, we don't want our pages to be too big. Why don't we want our pages to be too big?
And we could waste a lot of space and get a lot of fragmentation.
Which kind of fragmentation?
Internal.
Internal. With pages, remember, with page tables, we never have external fragmentation, only internal. So 4 kilobytes is a good size, 2 to the 12th. Why is it 2 to the 12th? How do you know it's 2 to the 12th?
It's 2 to the
2 to the 10th is what? A kilobyte. What's 2 to the 20th?
megabyte.
A megabyte. What's 2 to the 30th?
Gigabyte.
A gigabyte. So 2 to the 10th is a kilobyte, but this is 4 kilobytes. And what's 4? 2 to the 2nd. So it's 2 to the 2nd times 2 to the 10th is 2 to the 12th. So that's why it's 2 to the 12th. So a page size of 2 to the 12th. Page table would have how many entries? Well, remember, we take our address. He just did it by division, but remember, I'll show you pictorially what this means. If here's our 0 to 31, where's this imaginary line going? This imaginary line is going after 12 bits. This is the offset. The offset inside the page is going to have to be 2 to the 12. So that's 12 bits to 11, right? 0 to 11. 12 bits for the 4 kilobyte page size. So all the rest is the number of pages, right? The number of pages. So how many pages do we have?
2 to the 20.
Well, 2 to the, let's do what he says. He says 2 to the 20th, right? This divided by this is 2 to the 20th. Each 2 to the 20th, yeah. Page table would have 1 million entries, approximately, because 2 to the 20th is a megabyte, more than a million, right? It's 2 to the 10th is a kilobyte, 2 to the 20th is a megabyte. So we'd have a mega, not a megabyte, we'd have a mega rows.
Mega rows?
Yeah, our page table,
Like each row. is a
each
size.
row, we'd have from 0 to 2 to the 20th. We'd have a million rows in our page table. Now, how big is a page table? Page table's got to be at least, it's got to have in it which page to go to, right? Which means that each row has got to be 20 bits long, which is how many bytes?
Wait, but if the offset is only 12 bits, then shouldn't the size of the row be 0 to 2 to the 12?
No, this is not the offset. This is not telling you the offset. This is telling you which page in memory to go to, which frame in memory to go to. So each of these rows has got to be how many bits long? 2 to the 20th, right? Because I'm replacing, remember, I'm always creating a 32-bit address. This I'm cutting and pasting. This I'm taking here and I'm saying if it's 0, this whole thing is 0, then I go to the first one. But I'm going to I need to replace it with what I took out. So it's got to be 20 bits. It's got to be 20 bits. 20 bits, which is how many bytes? Well, byte is 8. 8 is 16, plus another 4. It's 2.5 bytes. So let's call it 3 bytes. So it's 3 bytes times a megabyte times right. This is a megabyte. So it'll be 3 bytes times a mega. So it'll be 3 megabits, or he calls it 4, right? If each table is 4, he says 4 bytes. I said 3 bytes. I said 3 bytes. He's saying let's round them up to 4 bytes. Each row is 4. Because remember, actually, they're going to have more things in it. They're going to also have the valid, invalid bit, right? So there's another bit. It'll be 21 bits. But it's really 3 bytes. But he's rounding up to 4 bytes. So it's 4 bytes. That means I'll have 4 megabytes for each page table, right? 4 megabytes for each page table. And I may have one page table for every single process. If I have 20 processes, just on the page tables, I've got 20 times 4, 80 megabytes of space. Well, that's not so much, but 80 megabytes of space for just the page tables. That amount of memory used, that amount of memory used to cost a lot. Used to cost a lot, okay. Don't want to allocate that contiguous. And then there's another problem, which is, well, actually, not another. How are we gonna, okay. I don't want to talk about the size. The more interesting is this second part. This thing is how big? We said it's 4 megabytes. Megabytes. How big is our page? 4 kilobytes, right? Our page, we said, is 4 kilobytes. How are we going to allocate this? Are we going to stick this? How are we going to access? When we say, oh, go here, if you look at our previous picture, how did we get, let's go all the way back. All the way back to this. This is the main picture you should remember. How did we get, we took this number and we used that to count down. If it's 4 megabytes, sometimes we'll count down, let's say 1 row. Sometimes we'll count down 4,000 rows. Sometimes we'll count down 2 million rows. Because remember, it's up to 4 million. Well, no, it's up to 1 million. So we'll count down sometimes 500,000 rows till we get there. But that only makes sense if this is contiguous. But we just got through saying that all of our memory is divided up into frames of 4 kilobytes. So the page table itself is paged. It has to be paged. We can't just count down, because counting down only makes sense if this is smaller than a page. How are we going to know where to jump to? We're going to have to page our page table. You understand? Because the page table is larger than a single page. Page table is 4 megabytes. So this page is going to have to be, we're going to take this and say, this is page 1, this is page 2, this is page 3, this is page 4, and we're going to stick them, we're going to have a lot of pages actually, and we're going to have a page table for the page table to tell us where in memory these pages are. So you see how we're going to get complicated. It's not complicated, it's the same logic, extending it one step further. And that's why I say we solve all the problems with abstractions. In other words, okay, so we're going to have to abstract now the page table. We have to say the page table, it may seem to be, in reality, no, it may seem to be contiguous, but in reality it's not contiguous. That we're going to make it, it's an abstraction that we say it's contiguous. In reality, it's not.
Can I ask a question on the diagram you drew?
I didn't draw it.
No, up there.
Yeah, okay.
Is each horizontal line another page?
No, each horizontal line is the address of a page. It's not a page, it's the address of a
Okay.
page. The address. So now let's look at this. Break up the logical address space into multiple page tables.
Are we having a break?
Oh, can I have a break? Yeah, let's have a break. Fine. Can I have a break? Stuff.
Till 11:05, 15 minutes.
Well, it's 14. Only set boys over 13, so.
You're okay.
Never had that problem.
No.
Yeah.
Kid, my parents think I'll be asleep for that long.
What if they heard in shul? See that in America, they hear Abdallah in shul,
Yeah, but if the
But
boys
then-
heard it, they didn't say it
But they didn't
themselves.
say
but
it.
they're Yotze. If they're the Yotze.
But I feel like they could
asked
still
my
say-
brothers
yeah.
because they didn't say it. They
Recording, share screen. Okay. So we were just saying that we need to page the page table. That's adding another level of abstraction. And I think that's what this picture is. Yeah. What is this? Hierarchical hash, okay. Yeah, so here's a page table. So here's the page table in the center. And the page table works like any ordinary page table. It tells you where pages are, right? Here is, for example, wait, let's look at this. Why these numbers are like this? Yeah. In other words, I'll go to the board. This is row, essentially this is the first section of the page table. This is the second section of the page table, and this is the third section of the page table. Normally, in the previous picture, we would have had these adjacent. There would be no gap, there would be no 3 dots in between. It'd be just all in a row. And if I want the first row, I go, I go to this row, then the second row, and if I get to the 10th row and I went to the 11th row, I just go to the next row. But here I got to jump. How do I know how much to jump? Because I got these pages over here. That's all we're saying. Once I'm on this page, obviously this page will tell me all the different pages that all the different frames that the actual pages are on. So it's actually quite simple. In other words, this is we call this an outer page table and an inner page table. The outer page table tells me where the pages of my page table are, because they're no longer adjacent, because they're too big. So I'm actually going to first have to go to this page table, and that's going to tell me, oh, you want row 11? It's the first page of the page table is here. You want row 12 already, so that's in the next page. So you got to jump down to line 100. Sorry, not to line 100. Here we don't see the numbers. This 100 is this 100. Where exactly this is in this page table,
What's the point of having the 2 page tables?
because I'll show you. What's the point of having 2 page tables? I'll go back again. We got to get a running start here.
But why?
Here.
More than one process.
Not because more than one process, right here. This is our classic view, right? Our classic view, here's our page table. How big is this page table? If this page table is small, then it can be that I count down P. If P is 6, I count down 6 and I get to row 6, and that tells me where the frame is. But what if P is not 6? P is 1,000,000 or 500,000. I have to count down 500,000. I mean, I don't count. I just jump to line 500,000. But the problem is line 500,000 is not after is not all in a row. In other words, this picture assumes that all these lines are one after the other. But if
you're counting down all the rows that are in the page table, whether it's grouped together or not, it's counting down the rows that are there.
But how do I know where to go? This page table is in memory, right?
But if you start
Let's say this
from
is
the top,
line. Let's say this is line 10,102. This is 10,103, 104. Oh, the page ended. That page of memory ended, and the next section of this is not at 10,104. It's at 20,107 because I've paged because I couldn't find in my memory a location where I can get all of this contiguous because it's so large. It's from 0 to 1,000,000, right? It's from 0 to 1,000,000. I got 1,000,000 lines. I can't, my pages, all of my memory, when I say my memory is paged, what I mean is that all of my memory is divided up into blocks of 4 kilobytes or 16 kilobytes, whatever it is. But it's not going to be divided up into blocks of 1,000,000 bytes. It's going to be blocks of, at most, I don't know, 4, whatever. Actually, maybe it could be 1,000,000 bytes, but whatever. It's going to be, let's say, it's 4 kilobytes. It's some small size. So when I go to my memory, I don't necessarily find a location to put the page table into. That's all contiguous. I have to divide it up into various pages. So now when I get to the end of the, let's say 4 kilobytes, and I get to the 4 kilobytes plus 1, I need to get to the next row, it's not right afterwards. It's a jump down or it's a jump up. So I need to know how much to jump down or jump up. And that's this picture here of a page table. In other words, I'm applying the same concept of paging, but I'm noting that I have to do it to the page table itself. page table. I'm just wondering why, wait a second. I don't know if I like this picture so much. I would prefer, what would I prefer? I would prefer there to be other blocks here. This is, what is this picture of? Is this a picture of physical memory or of
This is.
logical
this is
memory?
the logical memory.
the logical memory is safe.
Say it again, what? I think this is,
That's logical memory.
this is,
Well, where is the logical memory?
this is physical, I think this is physical memory.
But then physical memory that's saving logical. We're using it as logical.
We're using logic, this has gotta be physically sitting somewhere. This block, oh, here it is physically, right?
Isn't that the only physical?
Well, no, 'cause I thought the whole point.
No,
of-
1/500, right?
but
These are the
page table
pages.
is just a map.
In other words, normally, right, normally, here, let's redraw this a little bit.
You can pull the thing up so you can have more space to draw.
Oh, that's true. All right. This goes up like that, or I have to press it
Yeah,
up?
and then just let. Do you mind making the PowerPoint full screen?
Yeah. I don't.
In the bottom corner there is that way.
Thank you.
Master race. Okay, so normally our page table looked like this. I'm going to draw this box. 1, 500, 100, 708, 929, 900.
What?
Now,
Why are the numbers repeating? Repeating.
they're not repeating. No, I drew this again, but without the spaces.
No, but I'm just asking.
What numbers are repeating?
500 and then 100 and then.
Because this is not an order. It's not from 1 to 100. This is, let's add some more. This
That's
is
an add plus.
4,000. This is 20,000. They're just random numbers. This is 90. This is 3.
So those aren't the indexes.
This is,
those are the
right, this is
addresses
confusing.
sitting.
9, look, it's from up to down. Yeah, this is 825. They're just numbers. What do these numbers mean?
The address.
These numbers mean that I have my P and my D, right? Here's and the P comes here. And if P is, let's say, P, let's say, comes here. P is, let's say, let's label this 1, 2, 3, 4, 5, 6, 7. Yeah, 0. No, I forgot 3. 3, 4, 5, 6. So if P is 6, then I index is 6 in this array. And I go to row 6, and it tells me you want memory at location 3. You got to go. Sorry, you want location 6. You got to go to frame 3 over here. No, you're going to take the D. You're going to create this thing with 3 and then whatever D was. And you're going to go inside of frame 3 here. And then you're going to find D. Okay, this is, let's say 0, 1, 0, 0, 1, 2, 3. Yeah? So I said I wanted 6 in my why is it a P? Is it a P? Yeah, it's a P. Oh, for page. I want page 6, and it's really what I want is memory location 6 and 5, 65. So I'm gonna take the 6 part of it, the first digits, and I'm gonna say, go to line 6, and it's gonna say, oh, replace your 6 with a 3, and then leave your D the way it was, and then go over here, and there's your memory that you want. Now this is all well and good, except that if this page table is larger than page size, then I can't do this. Because I can't just count down 6 because it's 6, because it could be that 6 is already on a different physical frame. So you said it's a different, this is frame. These are, it's really, this is at, where was it? 100, here. Here. This is this line here, and then these sections, these 3 sections are actually not adjacent. So when I try to count down from the beginning, after I get to 3, I'm gonna go to somewhere, I'm not gonna get to 4. 4 is somewhere else. That's what they're trying to draw over here. That I count down, here's my 1, here's my 4,000, here's my 20,000, here's my 500, oh, here's my 500, here's 20,000, 500, and 193, and it's, and in between is some other, well, I want to call this a frame. Frame X, you know, frame Y. Some other program is sitting there. Some other information is in the physical memory at that location. So when I try to go down from here, I have to know this is going to tell me you want what we're going to do is like this. I'll show you what we're going to do. Let's take this example and let's say it really is 6, okay? So 6, how do you write, wait, I'm going to take this as 4 bits. I'm going to do it like this. 0, 1, what's that number?
7.
That's 5, right? No, that's 7. That's 7. So let's make it 6. Okay? Let's say it really was 6, right? 6 is a great number. So I want to go to 6. What does 6 really mean? 6 really means the first page, not the 0th page, the first page. And of that page, the second row. Well, because that's exactly what the 3 is. Look at the 3. This 3 is, this is the 0th page. That's 0. This is the second page, 1, the 1st page. And what is this row that I want? The 3 or 6s? 0, 1, 2, 2.
It just happened to be on the 6th row.
No, it didn't happen to me. I
No,
worked it
it's
out.
Be like that?
I worked it out.
It's always gonna be like that?
Yes.
You worked it out.
No, it's always gonna be like that. Yeah. I did it correctly. I mean, I'm just saying I did it correctly. It's always gonna be like that. We're gonna take, no, it depends on, we're gonna take the, what do I call this? The page number, and we're gonna divide it into 2 parts and say that part of it tells me which page of the page table, and part of it tells me in that page which offset.
So why
And
would
then-
you need that?
Because now I can do like this. Now I can say, now I can make this outer page table. What is outer page table going to say? It's going to say 0. This is place 0, place 1, place 2, and etc. And at place 2, I want page 1, which is this one, right? It's not gonna have 1 here to tell me that it's in it. It's gonna tell me where is 1 in the physical memory. So let's. In other words, this is in location 5,000. 1,000. This is in location 7,000. Yeah, this is in location 20,000, for example. So in my page table, I'm going to have written here 5,000, 7,000.
I'm telling you where's the page table.
Exactly. So when I want to know, so when I go look at this page number, that's my page number, right? So I'm going to take the first one and say, oh, that's 2. So I'm going to go to this outer page and say, sorry, it's 1. I'm going to go to the outer page and I'm going to go to this, to the row 1. Then I'm going to go, and it's going to tell me, change that 1 to 7,000. So now I'm going to say, oh, okay, I'm going to go to 7,000. Yeah, I'm going to go to 7,000, and at 7,000, I'm going to say, go to line 2. This is 0, 1, 2. And remember, I had 193. So there'll be a 3 here. That's the number you actually want. So now I'm going to replace this 3 into here. And now I've got the actual frame that I want. So it's 2 levels of abstraction. In other words, I need to get the page of the page. This is the page of the page table. This is the offset in that page of the page table. And once I got that, I actually know what the frame that I want is.
What if the page table is so long and there are more pages than the size of the page? Then you would need a 4 level.
What if there are more pages than the size of the page?
This isn't a perfect solution.
You're saying this outer page
It's not really
is, it could also not be long enough to get all of these. You're right. You're right. That's also true. It's also true. So we'll see. We'll see. There'll be limits to this. Yes. We may have many rows of page here, page here, page here. But let's see some examples. I think we have some more examples. Let me. Do you see, look, this is exactly what I just drew here. You see that? How the page number is itself divided into 2 sections? So let's read this slowly. A logical address on a 32-bit machine with 1K page size. So we're saying very small pages, 1 kilobyte pages. We talked about before 4 kilobyte pages. So 1 kilobyte page is divided into a page number consisting of 22 bits and an offset of 10 bits. Why is that? Does everyone understand why that is true? Why is it 10? Remember, it's the 22 bits is hard to get to directly. Always start with the offset. The offset, if it's a 1 kilobyte page size, they gave you that. So 1 kilobyte is 2 to the what? 10. To the 10. That means I need 10 bits. So that's why the offset is 10 bits. So I already can write that the D, that the offset section is 10. Whatever is left, if I've given that's a 32-bit machine, then I know there's 22 bits left. Okay? So since the page table is paged, so again, so we have 22 bits for the page table, for the page number. That means I have 2 to the power of 22. In other words, what is that? 4 megabytes, 4 mega page, it's not really megabytes, 4 mega rows, right? I have 4 mega rows of rows in my page table. Now, but since this page table is paged, the page number is further divided into 2 sections. And here is, now this is necessary. This part I need, this is important. This is an additional point which we need to understand here, which is that the offset is again 10 bits. Why is that? It has to be.
Is it because the page sizes are still the same?
Exactly. Did you understand the question and the answer? No. How did, notice he says here, since the page table is paged and the page numbers, then The page number is further divided into 10-bit page offset and 12-bit page number. Is that just random numbers? We could have said it's 2 and 20. Did it have to be 10 and 12? The answer is yes, it had to be 10 and 12. And I don't have to give you that on the test. I can just tell you it's a 2-level page and the page sizes are 10K. Once I tell you the page sizes are 1K, then all the pages, whatever page there is, it's 1K. You don't have different size pages. So if the page table is paged, it must be paged into units of 10K. There's no other size. So once it's paged into 10K, then it's got to be 10 bits for internally in each page. Whatever is left over is the number of pages that my page table has, right? So my page table has 2 to the 12th or 4 kilo lines, 4 kilo lines, right? Not kilobytes, but 4 kilo lines, 4 kilo rows are in my outer page table. Where P1 is an index into the outer page table, right? P2 is the displacement within the page of the, it's the offset within each page of the page table. This is known as forward mapped page table. Okay, I don't know why it's called that, but forward mapped. So here you just see a graphical representation of the same idea. This is what I drew already on the board for you. The P1 tells me which row in the outer page table to go to. That's the 2 to the 12th possible choices. Then once I got that, it doesn't tell me where the memory is yet. It just tells me which row to go to in the that just tells me jump to this page, jump to this frame essentially. I think this is a frame. Jump to this frame. And then in that frame, I use P2 to tell me go down this many spaces. And that will tell me the actual frame of the memory I'm interested in, or the actual frame that I'm interested in. And then I need to still use the D over here. Everyone's with me? I see everyone looking down. So I don't know if you're looking at.
P2 tells you which actual frame you're which next frame you're interested in.
P2 tells me which frame of the actual page table I want. But once I got the actual frame, it tells me how far down. No, sorry, P1 tells me which actual frame I want. P2 tells me within that frame which row I want. And now I've got the row, this gray row. And then that gray row tells me which actual frame the memory that I'm looking for is. But I still need to know in the frame where it is. That's D. And that tells me how far down to go. Okay? Now, let's imagine another example. This is just so you guys see how to do all of this work. And this is exactly, tell me your name again.
Leora.
Leora, sorry. Leora said, well, this can also be not sufficient. Even a 2-level paging scheme is not sufficient. And she's right. If a page size is 4 kilobytes, so now we're changing our example. We have a 4 kilobyte page. So how big is our offset? Well, before it was 1 kilobyte, it was 2 to the 10th. So now it's going to be 2 to the 12th. So it's 12 bits. Then the page table, now we're having a 64-bit logical address, not a 30. This was 30. We were talking here about a 32-bit machine. Now we're already up to a 64-bit, like a modern computer. And we have, wait a second, why is it 12? This contradicts what I said here before.
Yeah, because then the offsets aren't the same.
Huh?
Here, but I thought based on what he said before.
Yeah, I don't understand why it's not 12. You're asking my question? It should be 12 here. Wait, then page, wait, let's still solve it. If we have a page offset is 12, because that's what we're given, 4 kilobyte page. Then the page table has 2 to the 52 entries. That's a very large page table, a lot of rows, but it has to be because that's based on, what he chose is a fairly small, I mean, well, it's pretty normal size, 4 kilobytes is actually the most normal size, but it's still small size of a page table, of a page. So therefore, we're gonna have a lot of rows in our, and we have 2 to the 52, which is, well, 2 to the 30th would be a billion rows. This is 2 to the 40th would be,
That's higher than gigabyte.
Oh, it's just saying that.
yeah, this is not a billion, not a giga,
Is it a
Not-
tera?
it's more than a tera. It's whatever is more than a peta. It's a peta to the, it's more than a peta, because 50 would be peta. It's gonna have a lot of rows, not a million, not a billion, not a trillion, but whatever comes after trillion rows. That's how many rows each page table has, because we have a very large memory space, 64 bits, and we have very small page table, so we're gonna have a lot of rows. So that would be in a one level, we would have that many. But if it's a 2-level scheme, then the inner page table could be, here he writes, could be 2 to the 10,
And that's all the space that there is.
4 byte entries. Oh,
You can't fit more than
okay, look what he's saying here.
Is it because it's 4 byte entries? It is actually 2 to the 12.
Yes, this is interesting what he's saying.
Is he saying like word entries as opposed to byte entries?
Mhm. In other words, this is a subtle point here. I'm probably losing the, how do you say, 5/8 of class now. But yeah, when we need to reference inside of each page, we really just need a number for each row of the page. Let me put this up again. Where's the eraser? Oh. So our page size is 2 to the 12th. So that means we have memory. Let's, for convenience, let's draw it like this. So this would be byte 0, 1, 2, 3, 4, 5, 6, 7. Yeah, these are bytes. The total size is from 0 till byte number 2 to the 12th minus 1, right? That would be the whole page. That would be the whole page. So when we page that's a page. So when we make our page table, we have this very long page table, which is conceptually in logical memory. It's from 0. What is it from? It's from 0 to 2 to the 52 minus 1. Right? That's the 0 byte. These are the rows. These are the numbers of the rows. Whatever number I have here, it translates to a row in this page table. This whole thing. But I'm actually going to chop this up into pages. When I chop this up into pages, I'm going to say it like this. The row of a page is maybe has in it 4 bytes, because I need to locate a place in memory. Wait a second. I need to, when I finally find a page that I want, I need to generate a 52-bit address. How many bytes is 52 bits?
13.
Oh, wait, 52 divided by 8.
4 times 12 is 48, so plus 4 is 52, no, so that's 13.
No, it can't be. 80 divided by 8 would be 10. Right, so 50 divided by 8.
40 divided 6,
It's
so
like
it's
six-
like
six-
point. It's a little bit, I mean,
No,
it's
13, 52 divided by
7.
4 is 13.
When he's dividing by 8,
Oh, divided by 8, oh, not enough.
6, 6, it's between 6 and 7.
What? 7?
It's between 6 and 7. 48 would be 6, so 52.
Why are you dividing by 8?
Well, what I'm thinking is, here's what I'm thinking. Tell me if this makes sense. What I'm thinking is that eventually when I get this page, I'm going to need to translate it into a physical, into I need to get a frame number. And the frame number has to be this long. So that means in my row, in my page table, in other words, how big is this row? How big is this row? Doesn't it have to be, doesn't this number has to be from 0 to 51, doesn't it? I'm not used to dealing with such large numbers. Usually we talk about like 32 or less. This is a very large number, but I need to have 0 to 50, because I need to eventually do, take this and add it to my D. Here's my D, and here's my F, right? This is F, my frame. I need to add it to my D and get this address, which is our new address, my new 64-bit address, which is the actual location that I want. It's going to be frame number, whatever this is. These are 52-bit frame and 12-bit offset within that frame. So that means this row of the page table needs to have 52 bits. Each row has to be 52 bits long. It's 52 bits long times a billion, whatever it is, a trillion, a peta, whatever it is. I need all those. So it's going to be, and this you're saying is 7 bytes. What's 7 times 8?
56.
56. So yeah, so it'll fit. So 7. It needs to be 7 bytes long. So theoretically, I would need to have so when I chop this up, I don't know why, I'm trying to figure out why it's 10. I have to think about that a little more. But.
Oh, class is over.
Class is over?
Yeah.
Yeah, why wouldn't it be 12?
We stop at 11:45?
Yeah.
Yeah.
All right, so next time I'll give you a better answer on why it's 10.
Thank you. It's not even on. I know, I'm saying, 'cause it's still only gonna be on 21.